Hi everybody, welcome to my 6th torsional bar video. In this video I'm going to be solving a problem you see here. I'm going to be finding the internal torques, and then I'm going to be finding the angle of twist, and then I'm going to plot both of those. If you want to know something else about torsional bars, feel free to check out any of my other torsional bar videos. So the first thing I want to point out is the striking similarity between solving a torsional bar problem like this and solving an axial bar problem. Alright, the method of attack, if you will, is going to be exactly the same. Alright, because when we had an axial bar sticking out of a wall, we had some loads, some different diameters, different areas, alright, different modulus of elasticity. It's exactly the same here. It's like an equivalent problem, except in the torsional bar world. Okay, and you'll see what I mean as we go through this. So, I'm assuming if you're watching this video, you've already learned how to do axial bars. Alright, so you're just going to do the same thing you did before, except we're just going to do it with different variables. Okay, so the first thing to do, T1, T2, so that's going to be the torque in this section and the torque in this section. Well, like we did in axial bars, the first thing we do is make cuts to expose those internal reactions. Alright, so we'll have a cut 1 here, we'll look this way, we'll cut here, look that way. Okay, so this is section 2. So let's do a free body diagram of section 2. Alright, there we go. So note that I've drawn these, double-headed arrows. That just signifies a torque rather than a force. Alright, and now the same thing we do with axial bars. We're going to sum up the torques this time in the x direction to be 0. Alright, that's always the case for equilibrium. Then we can see T2 is equal to 100 Newton times meters. Box that off. Alright, note the very similar process as we did for axial bars. Alright, so for this free body diagram of 1, let me draw that out for you. Alright, so the same situation applies here. We're going to sum up the torques. The x, that's got to be 0. That's 100 minus 300 minus T1 is 0. Or simply T1 is negative 200 Newton times meters. Alright, there we go. So those are the internal reactions. Alright, so I just want to point out another time the similarity between an axial bar. Alright, if this was an axial bar, we had a force and a force, we would have gone through the same process and got the same numerical values. Instead of calling it T, we would call it N. Instead of Newton meters, we just call it newtons. So let's go ahead and plot these internal torques. Alright, so this indicates the end of the first one at 1.5, and then a whole 1 meter in between there. Right, from here, that brings us out to 2.5. So T1 is negative 200. So that's going to go right down here. And then T2, it takes us up to 100. All right, there we go. So that's the internal distribution, or the distribution of the internal torque. All right, two nice linear graphs. All right, so let's go on, and now we need to find the displacement. All right, or the angle of twist, and this is very simultaneous, well, not simultaneous, very similar to, delta when we do axial bars. All right, so if in axial bars, we use the equation delta is NL over AE, and in this case, we're going to use this equation. Phi is T L over GJ. So all these terms are like, they're sisters or whatever in a different world. So normals, the torque, length is the same. The area and the polar moment of inertia, they're the same. And E and G, they're their sisters in another dimension, if you will. So if you recall, when we did this, we also had this form of the equation. All right, and that allowed us to calculate delta when any of these things were varying. It also gave us delta if it was constant, right? Because when you integrate a constant, you just basically timesing it by that length. All right, and the same thing goes for phi. All right, so this differential form of this equation will allow us to calculate phi if any of these are changing or if they're not changing at all. All right, so typically if they're not changing at all, you're just going to use this form here. But in this question, I'm going to use this form just to get you guys used to the idea of these things changing. So let's go through. The phi at the very end, or the sum of all the phis, all right, so I can just say phi total, is equal to the sum of all the twists in between. So the total twist is equal to the sum of all the individual twists. So that's going to be the bit from here to here is some twist, and here to here is some twist. Each one of those pieces has a separate amount of twist due to their separate distinct properties. Alright, so we can represent it by going like this. So from x equals, taking x to start at the base, 0 to 1.5, that's the length of the first piece. The torque in that first piece, we call that 1 over G1, J1. Alright, so that's the twist of the first piece due to the properties of the first piece. Plus, from x equals, well now we're going from 1.5 up to 2.5. Alright, I'll let you see the picture again here. Because we're going from here to here, and if we start x from here, that's from 1.5 out to 2.5. That's going to be T2 in that piece, and G2, J2. Alright, now we don't explicitly know each of the components here. We need J1, J2. And we know that J for any arbitrary circular piece is pi by 32d to the 4. So I'm going to quickly speed ahead and calculate each of these for the two diameters that we were given. Alright, now that we know both of these two polar moments of inertia, we can sub them back into the equation, integrate, and solve for each one of these. So we can say that the total torque then, and now I'm just going to go through and evaluate these, realizing that everything in here is constant regardless of x. So it's essentially timesing T over Gj times this range right here. So I'm going to realize that and just evaluate it right away. Alright. Okay, and now evaluating each of these pieces, so we can see the elongation at the end of the first piece, and then the sum of these would be the total elongation. We get negative 0.001, this is radians, plus 0.005 radians. And the total then is going to be 0.004 rads. Alright, so let's plot this like we did before. Okay, now, like I said, the integration here, you integrate a constant, you basically times it by x. And when you have a constant times x, that's just a linear slope. Alright, so we know the values at certain points, and the lines connecting them then are going to be linear. So x equals 1.5, that's going to be negative 0.001. Alright, because this piece had to do with all the separate little pieces of, not elongation, twisting in this case. Alright, so the twist of the first piece is that much. This much here. Alright, so that goes down to here. Negative 0.001. And then at the very end, it's 0.004. So up here somewhere. And of course, these are all in radians. So I'm going to quick draw on the lines that connect them. Alright, there we go. And this gives us the visual representation of the twist of this bar as a function of distance. Alright, so that brings us to the end of this video. Hope it helped you guys out a bit. And we will see you in my next torsional bar video.